Hello everyone, my name is Salma and I work as a senior architect and I have Sharath with me working as a lead architect in NCS Singapore. We are truly thrilled to be here today to share how we have been leveraging event-driven architecture or EDA to assist our public sector clients in transitioning from a traditional system to a modern event-driven system. But before we get into the details, let me start by giving you a brief introduction to NCS and the work we do. In NCS, our purpose is to advance our communities by partnering with government and enterprises to harness technology. Now, we do this by bringing people together to make extraordinary happen. Now, combining the experience and expertise of its 13,000 strong team across 57 specializations, NCS provides differentiated and end-to-end technology services to clients with its next capabilities in digital, data, cloud, and platforms, as well as core offerings in application, infrastructure, engineering, and cybersecurity. NCS also believes in building a strong partner ecosystem with leading technology players, or be it research institutions and startups, to support open innovation and co-creation. Our strengths are in government within Singapore. This is our key differentiator. We are in a unique position to leverage these strengths for commercial enterprises across Asia Pacific. Now that we have seen that NCS is well equipped and committed to delivering with its extensive expertise in implementing event-driven architectures, let's move on to see the use cases we consider and how we prioritize robust security measures to address critical use cases that we see here. And that includes event-driven system, cybersecurity, modern application with real-time processing, and modern data pipeline. Let me share one of our experience of how we designed and implemented a microservices-based event-driven modern architecture, focusing on the two key use cases. Now, this ensured delivering a highly available and scalable solution that supports one of the critical scenarios of having a real-time and offline batch payment processing, which is all driven by events in a fairly large platform that caters other diverse applications and implementations as well. Having said that, we implemented event-driven architecture with microservices for a public tax organization in Singapore, where the solution facilitated a seamless transition from their outdated legacy system to a more resilient and scalable architecture. Our primary goal was scalability, ensuring that the system could handle high transaction volumes during peak periods. And the system needed to support high transaction per second or TPS rates that could dramatically increase at specific times of the year. We achieved an outstanding operational level agreement with over 99.95% reliability, meeting business demands. But we designed in a way that we carefully segregated workloads between cloud and on-premises network, ensuring optimal performance and security. We also liaised on private link to ensure secure communication between systems, leveraging the power of public cloud for isolation. Now, this architecture effectively supported both real-time processing and offline bulk processing use cases, which was a critical piece in their overall business, delivering speed and reliability across the platform that involves multiple other integration between different sources and destinations. The diagram here showcases how microservices interact in an event-driven architecture, where producers generate the events and consumers that are located on the right react to them. The core of this system is the event broker, which ensures a very reliable communication between these two. These microservices on the left generate specific type of events, say event A, B, or C, based on their business process or system activities, and the microservices on the right, which are typically the consumers, subscribe to these specific events. And the central piece of this architecture would be the event broker, that routes events from the producers to the appropriate consumers. Now, this ensures decoupling by enabling producers and consumers to completely operate independently without needing any direct connections. For example, one consumer, which is located on the right again, is subscribed to both event A and event C. Another listens only to event B. And a third seems to be subscribed exclusively to event C. Now, the key benefits of having this kind of architecture would be scalability, where producers or consumers can be added without affecting the existing system. And this makes it highly scalable and stable. Also, producers and consumers do not directly depend on each other. Allowing independent updates or changes that decouples them, and the event-driven system enables consumers to subscribe to any combination of events, enabling diverse and adaptable workflows. To complement the architecture, a disaster recovery environment is made available in a passive state with synchronous replication from the active environment to ensure a high available architecture on a whole. Now, this shows one of our critical use cases for a payment service that could either be online or offline as a bulk. The offline transaction process relies on a bank CFT file received on a scheduled basis. The microservices here are decoupled based on the functionalities, but it caters both for online and offline payment services. So here, the bulk processing microservice subscribes to a message event that generates a patch ID for the job, and it publishes a message event containing the source ID to indicate if it's an online or an offline type with a reference ID and other details. A similar flow is implemented for online payment scenarios where transactions are triggered from UI and follows a comparable event-driven architecture. Now, this event is consumed by the Gyro microservice, which triggers the downstream microservices by publishing the message events with the same identifiers to initiate their respective process. Now, each event also includes traceability indicators such as a record ID as a part of the event message for tracking purposes. Now, the downstream microservice, such as the payment microservice, reports back to the bulk microservice or online microservice by publishing the job statuses as a message event. Events are also further sent down to enable updates using the ledger microservice and correspondent microservice for notifications. Now, all these microservices are empowered with CADA that can monitor the events and its consumption rate and check for any lag indicating the difference between the messages produced and the messages that are being consumed, and apparently adjust the number of pods accordingly. Since scaling is directly tied to the events here, it ensures rapid responsiveness to workload changes. Now let's walk through some critical design considerations and their desired outcomes for building a robust event-driven architecture, which NCS follows as the primary guideline. The first consideration would be the overall platform design that must prioritize a high available architecture. Now, this can be accomplished by implementing active-active clusters or active-passive configuration. Furthermore, a disaster recovery environment is essential to replicate clusters and ensure continuity in the event of failures as demonstrated in the previous slides. Further, the capacity planning should also be done effectively, determining the number of producers and consumers based on transaction per second. It also considers the expected throughput to ensure sufficient processing capacity and plans for storage and retention to manage persistent data effectively. Now, this includes the infrastructure and sizing planning way ahead. We will deep dive into this for a basic guiding principle in the subsequent slides. Now, additionally, the design of topics, producers, and consumers is also critical in an event-driven architecture because they form the foundation of how data flows and is processed in the system. Like, for example, the topic design does play a crucial role in determining its scalability with certain key considerations like the number of partitions, for horizontal scaling, a partitioning strategy to avoid resource bottlenecks and ensure even data distribution, or setting a replication factor for fault tolerance, or defining a retention policy to meet data governance requirements. Further, producer design ensures that efficient message and batch sizes for optimal payload delivery is being set, with proper acknowledgements to confirm the message delivery. And the most important one would be the idempotency to make sure the duplicate messages are prevented. And all in all, to have a robust error handling to mitigate potential issues. Now on the consumer side, we do focus on duplicate handling and how the offsets can be managed effectively to track committed messages and organize them as consumer groups for efficient load distribution and again scalability. Now, by considering these factors, we can design a resilient and scalable architecture to meet any operational and performance demand. Now, let's discuss capacity planning and sizing to ensure that the system can effectively handle its workload. Here, we provide a high-level approach to derive certain key metrics. Starting with inputs such as the number of microservices and their payload sizes, we can apparently calculate the cluster size and the expected throughput, which will help guide the system's resource allocation and scaling requirements. Now, this process ensures that the infrastructure is adequately designed to support any operational demands while maintaining performance and reliability. Now, the input on the left corresponds to the derived outputs on the right, serving as a foundational template for effectively determining overall capacity. With that, I'll hand it over to my colleague Sharat to continue. Thank you.
Hello everyone and thank you Salma. For those who may have just joined, my name is Sharat. I'm a lead architect in NCS Singapore. Today I'll walk you through one of the use case and the technique we employed at one of our public sector clients and how we helped them transition from traditional systems to become a modern event-driven systems. In the course of next few slides, we talk about overview of the use case, discovery and the EDA approach, use case workflow, EDA benefits and challenges, and the summary of the use case. This slide talks about transforming port authority operations with event-driven architecture. To give you some of the context and background, NCS was engaged by a prominent port authority in Asia-Pacific region to improve their operations, bring in flexibility, agility into business operations. Being a large port that handled high volumes of messages, this port faced many challenges in carrying out their day-to-day operations. Below are some of the current system challenges categorized into architecture, integration, operational, and monitoring challenges. The goal of this use case was to implement a fully driven, event-driven architecture that enables real-time coordination, scalability, and brings in resiliency into port operations. This slide talks about the initial discovery phase, where we identified that most of the existing system architecture at the port was based on client-server architecture. A model heavily dependent on centralized database resulted in tightly coupled rigid monolithic systems with issues in scaling and performance. Hence, it was important for us to identify key systems and key events to logically separate them from the monolithic systems and stitch them together with event-based workflow without any impact to port authority workflow logic. This slide talks about implementation of event-driven systems and its coordinations with event-based workflow at port authority. A series of events generated form the workflow logic. For instance, when a vessel arrives, a vessel arrival event is published onto the event bus. This event is subscribed by port operations management, vessel arrival, and cargo handling systems to mark the beginning of port authority operations. Vessel arrival systems can further place a synchronous call to custom clearance systems to check whether the vessel has been cleared by the customs. Once customs are cleared, a custom clearance operation event is published onto the event bus. This event can be subscribed by cargo handling systems, and the cargo handling systems can start the loading and unloading operations. Further, The events generated during the Port Authority operations can be subscribed by the Port Operations Management Systems to generate notifications and inform various stakeholders to receive real-time updates. On taking a closer look, you can visualize that resulting systems or event-driven systems can publish and subscribe to events equipped with business functions that can independently work to execute business logic by simply subscribing to interested events. Adapting to event-driven architecture was challenging. Applying well-documented design principles can make it easier. Here are key design considerations that have helped us for successfully implementing EDA systems. Some events must occur in a specific sequence, example, vessel arrival followed by custom clearance or cargo unloading. Handling complex event dependencies and ensuring right sequence of operations is a challenge. Hence, importance need to be given to event ordering and their processing. Ports need to manage eventual consistency across systems like vessel scheduling and cargo handling, when delays in one system can impact the entire process. Port Authority might have legacy systems that need to be integrated with event-driven platform, requiring careful approach to migration and synchronization. In a distributed event-driven system, it is crucial to have robust monitoring tools to track events in real time, detect failures, and ensure the systems are processing in events in a timely manner. Given the sensitivity of port data, example, shipping manifest and custom data, security measures like encryptions, access control, and audit logging need to be considered for the event streams. The benefits of EDA are numerous, but I'd like to highlight the scalability, resiliency, flexibility, and adaptability of event-driven systems, which align with Agile principles to enable continuous improvement and responsiveness to change. Here are some of the key benefits. Subscribing to different events allows systems to react instantly, improve operational efficiency, and reduce system bottlenecks. As the port handles increasing in traffic and complexity, systems and services can scale independently. Each system operates independently. If one system fails, others can continue functioning, allowing for better fault tolerance and recovery. Processing failures in one part of the workflow can trigger automatic retries, send out alert events, ensuring minimal delays or downtime in operations. With all events logged, Port Authority can analyze trends and optimize processes for efficiency and cost savings. Event-driven systems are highly adaptable, enabling the port to seamlessly introduce new technologies or systems, such as advanced cargo tracking or automated custom checks, without disrupting existing operations. This flexibility supports rapid adjustments to change in market and regulatory conditions. This slide attempts to summarize the modernization of Port Authority operations with event-driven architecture and how it enabled system evolution by aligning with business goals. For instance, we could quickly identify a group of systems and move the systems to cloud with lift and shift approach to align with companies' cloud migration strategies. We could quickly optimize disaster recovery plans and segregate traffic between east and west data centers. Make rapid adjustments to changing market and regulatory conditions to allow systems seamlessly integrate with new systems or technologies without disrupting existing operations. It goes without saying that we could achieve all this by picking right platform to route events across data centers and deploy microservices linking systems across hybrid data centers by building event mesh and service mesh. We implemented event mesh using Stoles platform. We implemented custom service mesh using Java platform. With that, we come to an end of this slideshow of this use case. Please reach out to explore how NCS can help you with your EDA journey. Thank you.